That's probably a pretty good idea.
Whoa. Terrifying. So I've got a small population for you here, 6 elements. And those 6 elements, they're randomized. I like random. I like random because it lets me see patterns if patterns exist. If I keep letting things random through, then I can actually tell if something's happening coincidentally or generally. And what I've done down here is I've placed some parameter values. Let's do a quick review and make sure I remember what all these things are. Mu. Who's that? That's your average. That's your arithmetic average of the population. So if you took all of these, added them up and divided by 6, you'd get that guy right there. Perfect. How about MED? Median. That's your median. Mind me what that one is, median. Good. Middle number when the data is... Right, but we have to do the data first. These 2 middle numbers right here?
Put them all in order.
Good. Gotta be in order. Gotta be in order. And that's why it's important to say that, because you have to make sure that they are at least the greatest to get the median. Sometimes that ordinal data I mentioned earlier, sometimes people try to take a median of it. That makes me less nervous than an average, but still nervous, because you're implying median doesn't care about space between data points as much. So when you put things in order and then find the middle, you are technically finding the middle of the values. But the implication that the numbers themselves can be ranked is still out there in my mind. But it's less than the average. This is kind of hard to see. It's a little sigma. Do you remember that guy? That's your population standard deviation. I very rarely mention that in 243 because we very rarely had it in 243. We talked about samples more than anything. This is the square of that. You remember what that's called, Donna students? I didn't talk about it much at all in 243. Okay, variance. It's the square of the standard deviation is the variance. The reason you never talk about it, good, I'm glad she doesn't, is because it really doesn't have any practical application for you guys. It's got a great theoretical one today, and we're going to use that and then run away from it, once we know it's there. This is the proportion, little p, from the binomial distribution probability. This is the proportion of the data that are greater than 0.5. I just decided to use a half as a measure. See how it says 0.83 right now? If you look at that data, 5 of the 6, or 83%, are greater than a half. 0.67, 0.57, 0.6, 0.63, and 0.66. The 0.12 is left. And if I hit a restart, we'll see. Now it's at 0.33, excuse me, now it's at half. That means half of them are bigger than a half, and the other half are smaller. So bigger than a half, bigger than a half, bigger than a half, smaller, smaller, smaller. Hit it again, now it's still at a half, smaller, smaller, bigger, exactly equal, which I'm guessing it's counting as bigger. Actually, it's not exactly equal. That's rounded off. So that's larger, larger, small. Does anybody kind of see what that's going on there? It's just keeping track of which ones are larger than 0.5. The average deviation is just another measure of deviation. I mentioned it way back in the day in 243 and then stopped talking about it, and that's okay. We can forget about it too. But you'll see why we're going to forget about it today. The mode. What's the mode? The mostest. The mostest. Why does mine say not applicable? Why does mine say not applicable? It says NA, not applicable.
No numbers are
Exactly, Chris. There's no mode up there. They're all different. As a matter of fact, you'll they got one that time, 0.83. But very rarely do you get a mode, 0.78 that time. Okay? Not very many times do you get a mode with data like this. Okay? The range, something I talked about, again, beginning in 243, just the spread of the data. And then the skew, which I made you guys deal with in 243, and this is one of those vomit-inducing topics. Pearson's skew coefficient. I remember making you guys calculate this, and you got so peeved. But I want to bring it back up because I think it's important. Now, what I've done in each of these 9 graphs, it's a little bit hard to look at, but you get the deal. In green triangle represents the value of the parameter, if it exists. The mode doesn't exist all the time, so therefore it's not there. The value of the parameter represented over here. So right now the average looks like it's about 0.45 maybe. Yeah, 0.46. So it's right about there, 0.46. The median's here at 0.43, 0.43, and so forth and so on. And that's for all 9 boxes. All right? Good so far? Good so far. In red, well, let's do blue first. In blue, what I've done is I've used Excel, and you can kind of see where I've done it back here. All those little green triangles, letting me know there's calculation going on in the background. I've taken every possible sample of size 2 from this population. So, I sampled 0.3 and 0.3, 0.3 and 0.76, 0.3 and 0.28, 0.3 and 0.31, 0.3 and 0.56, 0.3 and 0.54. 0.76 and 0.3, 0.76 and 0.7. Okay, it's going to get annoying. But that's what I did. 36 samples in all. 36 samples in all. And then I've taken these parameters, well, not parameters, the statistics of those samples. So I took X bar for the first sample, X bar for the next sample, X bar for the next sample, X bar. So 36 X bars, 36 medians, 36 sigmas, 36 sigma squares. Sometimes they're the same value. Sometimes you get repeaters. That's what the blue marks are. The blue marks are each of those individual statistics measured and plotted. And you can see they're all over the place, as you might think they would be, right? I mean, imagine if you pulled the average right now of this population, and you pulled 0.76, 0.76 versus 0.3, 0.3. Well, one of the averages of that is 0.76 and one is 0.3. So you're going to see one average way over here and one average down here, as you do. Is that fair? That's natural variance in the samples, and that happens all the time. It goes back to our question about Gallup. 9% success rate. How do we know that 9% is accurately targeted? Here's how, right now. The red square is the average of all of those samples. So if you take all of those mathematical values of all those blue triangles, all those blue squares, diamonds, whatever they're called, and you average those values, you get the red square value that's here. Am I doing this? God, no, Excel's doing it. Thank God, right? Now, do you notice how 3 of the rectangles are yellow up there, and the other 6 are white? Why did I make those 3 yellow? And I'm gonna hit F9 a few times so you can watch the dance of the data. You see how those little triangles in the background are reformatting each time?
Average of the samples is the same as the parameter.
Will Downing, please say that louder.
The average of the samples is the same as the parameter.
Holy crap. Holy crap. The average of the samples. I made up a name for this, by the way, in 243. Last year, I called it X double bar. The average of the averages. I called it X double bar, and you guys were like, oh my God, is this class over yet? I remember. A couple of you vomited. The average of the statistics. So the average of all those averages is the same as the parameter value. The average of all those variances, sample variances, is the same as the parameter sigma squared. The average of all those proportions, and there aren't very many proportions. There's not many you can have. 1, 1/3, 2/3, and 1. Or excuse me, 0, 1/3, 2/3, and 1. But the average of all those proportions comes out to be the parameter value. Not the other ones. Or I should say, not generally in the other ones. Sometimes coincidentally they do line up. The medians aren't usually very far apart, but they're not exact. They're not exact. The modes, as you can see, the mode sometimes doesn't exist in the population, but the samples can definitely have one. You see, you got skew, you got some skew, you got some skew in the skew. Equal, not equal. Equal, not equal. And this happens every single time. And look, as I press F9 each time, it's almost like that red square and that green triangle are tied together. And they are tied together mathematically. Now, if I was a lesser educator, I would have cheated and just made the green one and the red one have the same Excel cell. But I don't. You have this spreadsheet, you will have this spreadsheet. You can analyze it yourself and see what the hell I did. And if you want proof of why these 3 things match, it's on that enrichment page of the website. So if you're having trouble sleeping this weekend, it'll be 3 o'clock in the morning on Saturday, go tune into that. That'll put you right out. Put you right out. But here's the deal. Let's close this thing down. Will Downing, thank you for that connection. That was wonderful. We're going to go back to here. This is why we're here. Now, I'm going to have this posted for you guys. So you don't feel like you have to write this stuff down. It's not crucially important to write this down because we're going to use it today. You're going to have it. There are only 3 parameters that behave in the way Will described. Only 3. Mu, which is targeted by X bar, our sample average. That's why we spend so much time in 243 building the sample average, the central limit theorem. Sigma squared, which is targeted by S squared. We didn't spend almost any time at all with that guy back in 243. And the population proportion, which we call little p, we're going to spend a lot of time with him today. P hat. We like p hat. P hat's our friend. That's a sample proportion. I used to say p hat a lot. I had a bunch of nurses one year, and they kept chuckling. They said, p hat, p hat. I'm like, all right, what the hell's so funny after the third week of hearing chuckling? And they said, apparently, they have this thing called a p hat in hospitals. You shave a little pilgrim hat, you put it in the toilet for a urine sample. And they made me one. They put little p hats all over, maybe wear it in class. Whenever I said I had to wear the damn hat. P hat, get used to it. It's like X bar, but it's like X bar for discrete data. X bar is, if you will, for continuous data, and p hats, if you will, for discrete data. That's the easiest way to kind of keep track. If you have to take an average, it's usually of continuous, and if you have to take a proportion, it's almost always of discrete, because you can't really count continuous data. Now, here's a gift. One of the things I cut from this course was the analysis of the population variance through the sample variance. Why? Because Oregon continues to have 10-week terms versus 16-week semesters. And it's crude and rude to shove that down your throat in 10 weeks. It makes much more sense, in my opinion, and pedagogically, my folks at OSU and U of O agree with me on this one, to spend roughly half the term analyzing X bar and half the term analyzing p hat, or, if you will, mu and little p. It makes them much happier, because if I spread it too thin, and I think spreading it too thin is what happens, you get less depth on more topics, and nobody learns anything as well as if we can cut it back. So if you look at the syllabus, you'll often see the word proportion, mean, back and forth, and back and forth, and back and forth. And I keep it that way because I want to focus on just those two. So, because I don't have enough time, we're going to drop the variances off. Fair enough? Please, Rach, go.
So you said that the unbiased estimator with the average and the p-hat, that's for discrete data? What was the other one?
This is generally discrete. This is always discrete data. That's continuous data.
Oh.
Usually, you can average discrete data. You can. I'm going to show you how to do that in this class. But this has to be discrete. And this is usually continuous. Just by definition of the data we're usually collecting. Please, Caleb.
What is discrete data?
Good, great question. What is discrete data? How do you get discrete data? What's the collection method? It's been a long time, it's 2:43, I know. It's been like a long, 13, 14 weeks. Do you measure it?
You count it.
You count it. It's counted data. So when Gallup does a poll, Congress is now less popular than syphilis. Okay, because the syphilis infection rate is 10% and the Congress approval rating is 9%. What they did was they asked 1,000 people. They asked 1,000 people, and 90 of them say, yes, Congress is doing a good job. 90 over 1,000 is 90%. But they counted those people. That one said yes, that one said yes, that one said no. This 100 people said no, yes, no, yes, counted. If I was interested in the average weight of, say, a newborn on a certain formula versus a newborn on some competing formula, that'd be continuous. Because how do I get weights? You measure them, you put the baby on a scale, and the precision of your device. So basically, counted data is here, always. Measured data is most often here, although you can average discrete data. You can, and we'll see how you do that. And I've got an experiment we're going to do in this class.
So measured is called continuous?
Measured is continuous, my friend, and
is...
counted is called discrete. Yep, and I'll keep those terms rolling all term because it's important. It's important to know what to do with what. One of the things that drives my students nuts is on assessments, I don't tell you which tests to run. I give you data and say run the proper test. And you get used to it because you start to recognize the data. You're like, okay, it's a percentage, so it's probably 99.99% of the time it's going to be discrete because a percentage is something out of something. And as soon as you see things like weight. So here's some key indicators. For continuous data, generally 4 things are continuous. Do you remember the 4 are from 243? I just mentioned one of them. Height is one, good, or distance, you call it distance. Height, distance. I mentioned babies, weight, height and weight. Time, very nice. And I mentioned this one earlier today. Temperature, thank you, Eric. He's back. He's back. I'm not sick anymore, he's back. Temperature, time, distance, weight. Those are the four continuous data types. I can't find any more. I can't think of any more. I mean, some people say like volume. Volume is continuous, but volume is just length cubed. So it's another subdivision of length. So if it's not those 4 things, it's probably counted. Good! Speed or acceleration, distance over time. Right? It's a rate, so it's a distance over a time, so it's made up of two continuous units. Awesome. No, but it's definitely continuous because of that. Kaylee, thank you for that question.
Yeah.
Sometimes I forget those kinds of things. I forget
It's been a long
that.
time.
No, it's been a long time, but you see, everybody used that. That was perfect. And now we have even better idea of continuous versus discrete, and we're going to be doing it here. Thank you. Let's take a pause. That was a great response. I'm going to pause this. Let me take one more roll.